Okay, what I want to talk about in this video is something about compound statements. That is forming new statements from old statements, and that will be done using some symbols known as logical connectives. We'll come across that a bit later. But let's say for now I have two statements P and Q. I'm denoting it from small letters. As P is one statement, Q is another statement. So we can make compound statements using these two statements. But even before that, there are just a handful of possibilities for these for the truth value of these two statements, right? I can have either both of them to be true. So in that case, both of them are true. I can have P to be true and Q to be false. I can have a P to be false or Q to be true, and I can have just both of them being false. So these are the only four possibilities when you have two statements. So either both of them are false, either P is true, Q is false, either P is false, Q is true, or both of them are false. So the first type of compound statement that we'll come across is the AND, is using the logical connective and it's denoted by P, this upside down V symbol Q, and it stands for AND. So if you have a statement P, if you have a statement Q, you can make another statement. This is, let's say, this is the new statement R, which is just P and Q, and it is very much in parallel with the English word and that we know. This statement will be true if both P and Q are true. So if you have P and Q to be true, only then will this statement be true. If you have any one of them to be false, so in this case Q is false, then in that case this compound statement P and Q will be false. If you have here P to be false, even if Q is true, it doesn't matter. The whole statement will become false. The compound statement P and Q will become false. And yeah, of course, if both the statements are false, P and Q gives you false. It comes out to be a false statement. The next type of compound statement that we have is or statement. Again, it's very much in parallel with the English word or that we know, and it's denoted by this symbol. It's the upside down version of and, P or Q. And again, I can say this is a new statement S. I need not even write that. This is a statement P or Q, and it makes logical sense that this should be true when at least one of the P's or Q's is true. So in case both of them are true, then this is very much true. In case P is true, Q is false, I can say P or Q is true, because at least one of them is true. Also here, if P is false, Q is true, at least one of them is true, right? Q is true. So I can say that the whole statement is true, P or Q. But if I have both the statements to be false, there's no hope. Neither P nor Q is true. So this evaluates to false. So you can say that the AND statement is true only when both of the statements are true, and the OR statement is true when at least one of them is true. So in that case, this was also true, right? Okay. The next kind of I would say pseudo compound statement, because this does not give you, this does not use two statements. It just uses one statement. It's using the logical operator of not. Usually denoted by a little tilde, and it is operated on just one statement. So I can say tilde of P or not of P, and it basically evaluates to the opposite of what your statement is. So if your statement P is true, then this will evaluate to false. Again, in this case, it will evaluate to false because your statement P is true. If your statement is false, then not P will evaluate to true, and also not P will evaluate to true. You can do this with not Q as well. I've just taken this as an example. But this is kind of a unary operator. It just requires one statement, in contrast with these binary operators. These require two statements. The other kind of compound statement that you can form is using the if-then logical connective. If then. So, and it is denoted by this symbol P implies Q. So here you can say that P is the premise and Q is the conclusion, or P is rather the information that you have, and Q is something you can conclude from this information. So this if you have P to be true and Q to be true, then this if then statements P implies Q. This is again a statement. I can say this is a statement T. This whole statement is another statement T. So this evaluates to true in this case, if both your premise and your conclusion are true. If your premise is true, but your conclusion is false, then this if then statement evaluates to false. Now here it's a bit interesting. If your premise is false, then no matter what your conclusion is, your if then statement will turn out to be true. This is a huge misunderstanding that a lot of people have, that how can the statement evaluate to true if your premise is false? But it makes logical sense, because if you are assuming that what you are saying is false, then anything you say about the conclusion is true, right? Because you are starting with something that's wrong. So anything that you can conclude, you can say it's true, right? If the premise is itself false, then no matter what the conclusion is, I can even say that in this case, the if-then statement is true. So if my premise is false, no matter what the conclusion is, the if-then statement comes out to be true. If my premise is true, but the conclusion is false, in that case, I get a false statement for if-then. And of course, if both the statements are true, then I get a true statement. And the last kind of compound statement that we have here is it's kind of this, but it's both ways. So if and only if, I'll denote it with I double F. It's shorthand notation for if and only if, and it is denoted using a double-headed arrow. P if and only if Q, and it's kind of a double condition or biconditional. Uh, Okay, let me tell you the formal names of all these logical connectives. This is called the conjunction. This is the disjunction. This is the not negation. This is the conditional, and here we have the biconditional form. And we'll come across the connection, the connections of all these kinds of compound statements a bit further. But this is kind of just the definitions for each and every type of compound statement. So P if and only if Q, this evaluates to true only if both P and Q are same. Now, no matter what they are, they have to be same. So if both P and Q are true, in that case, I will get a true statement. If both P and Q are false, even then I'll get a true statement here. But if one of them is true and the other one is false, I get a false statement. Here one of them is false, another one is true, I get a false statement. So yeah, this is kind of the truth table for all the logical connectives, the compound statements that we can form using two statements. And you can, if you want, you can extend this to three statements. If you have three statements P, Q, R, then yeah, mind you, there won't be just these much possibilities. There will be 8 possibilities, and you can generalize it to the statement that if you have n number of statements P, Q, R, S, T, and so on, then your number of possibilities, your number of rows will be 2 raised to n. So if I have another statement here R, it's not this one, it's another statement R, then my number of possibilities will be 8. It will be all true, 1 true, 2 false, and so on. So you can generalize this to n number of statements, but this is kind of the basic structure for each and every compound statement that we'll have to use.